Gosh, you back on?
Okay, ready.
Okay, great. Thank you. Gosh. Looks like we got a great participation. We got over 90, close to 100 attendees on this talk. Title is LiDAR for Autonomous Vehicles, and this presentation will be given by Dr. Khanna. Just like to welcome everyone. I think we have a global participation as well as a number of folks on Facebook. So next.
Will we be able to get a copy of the slides?
Okay, we'll answer any questions that anyone has at the end of the presentation, if that's okay with everyone. We'd like to keep everyone muted at this point. So let me just dig straight into it. This is an MTTS presentation. The meeting is being recorded and broadcast both on Zoom and Facebook. Links to the recorded video and slides will be made available to all registrants, and we'll send out a link within the next couple of days. Please keep cameras off and microphones muted. This helps with the bandwidth issues and keeps the background noise low or acceptable. So, and then as I mentioned, we'll respond to any questions that anyone has. If you do have questions, use the chat window to everyone, and we will take periodic breaks in between and choose, go through the questions as they surface. Next. Please ensure that your display name in Zoom matches the one you use to register. This will make it easy for us to check you in as we move along. If you did not register and were forwarded the link to this meeting, please send it to Krishna, a private chat message in Zoom with your name, email address, and IEEE membership status, with your non-IEEE, IEEE, or IEEE plus MTT, so that we can register and check you in. Next. Okay. So again, we like to promote the MTT Society. We are a member-driven society. And the chapter activities are volunteer-based. Become a member. I mean, there's a lot of things that this society offers. So this is a link to it. The IEEE, IEEE.org membership, and the MTT is a global organization, and we have chapters throughout the globe. So check the website, and it'll detail the closest chapter that'll be close to you. Next. The agenda is just a quick COVID update. This is a joint talk, and I apologize I didn't mention the Circuit Society. That's also co-sponsoring this with the Photonic Society as well. So I want to thank those societies for supporting this talk. We'll go through the MTT Santa Clara Valley offices, and then our vice chair will go through the speaker's bio, today's talk, and then at the end of the talk we'll have the Q&A. Thanks. So I'm sure everyone is aware with the COVID-19 pandemic, all our personal in-person meetings have been relegated to online. Monthly technical meetings and office meetings will continue on an online webinar format only until further notice. Next. So again, just to underscore the folks who are sponsoring this is the MTT Society, the Circuit and Systems Society, and the Photonic Society as well. And all of these three organizations reside under the IEEE logo. So the chapter chairs, I'm the chapter chair, Jay Banwaite. Vice chair is Utkarsh Krishna, we heard earlier. Secretary is Tan Tui, and our treasurer is Tom McKay. Next. So Utkarsh, I'll ask you to introduce our speaker.
Thank you, Jay. It's my great pleasure to do so. So before I go into what's written up there, if you've been involved in microwave at all in any form over the last few years, if you've been involved with the MTT or if you've been involved with, especially with IMS, chances are that you've either heard of, worked with, or know of Dr. Amarpal Paul Khanna. Welcome, Dr. Khanna, and thank you again for agreeing to do this talk. It's a great pleasure and honor to have you here with us. So Dr. Amarpal Khanna is a life fellow of the IEEE, and he was till very recently a distinguished engineer at National Instruments, where he was my colleague. So Paul was instrumental in advancing NIS capabilities in microwave, millimeter wave, and optics technologies, particularly for applications in automotive radar, LiDAR, and 5G test and measurement solutions. He has also overseen the R&D of components and custom subassemblies up to 110 gigahertz and RF over fiber subsystems. Prior to NI, he held several leadership positions at L'Oreal, Avantec, HP Agilent, Teledyne, and at Face Matrix, where he was a vice president. And that just underscores what I said earlier. He's been around the block, and if you've been in the microwave domain, if you worked in the microwave domain, chances are you've run into him. So he received a BSc in Electronics and Electrical Communications from Punjab University in Chandigarh, India, and his master's and PhD degrees in microwave and optical communications from the University of Limoges in France. He was the general chair of the IEEE IMS conference in 2016 and has been the leader of several IEEE MTT subcommittees, both technical and organizational. He's presently the vice chair of IMSEC, amongst other responsibilities, with more than 60 papers in peer-reviewed journals and conferences, 7 US patents, 2 European patents, and many contributions as a teacher, mentor, and organizer. Paul is world-renowned, both for his technical contributions and for his IEEE work. So a quick introduction to today's presentation, the title of which is LiDAR for Autonomous Vehicles, the Principles, Market, and Trends. The ability to move people and goods safely, efficiently, and reliably is becoming a critical need in our fast-changing world. Self-driving vehicles, or SDVs, promise a new way of transportation which has the potential to eliminate accidents caused by human errors and free up vehicle drivers. Several technologies are used in vehicle perception systems to detect the presence of vehicles, people, and other moving or fixed obstacles. These include camera, radar, and sonar sensors. LiDAR is a new addition to complement the existing set of options and offers unprecedented resolution, accuracy, and imaging quality. LiDAR has started being used in SDVs, but considerable challenges exist for mass production and use. Among the different types of LiDARs, the common ones are TOF, which is time of flight, FMCW, that's frequency modulated continuous wave, and flash. Main components of a LiDAR sensor include laser source, beamforming and scanning unit, and photo detectors, among other technologies. The technology landscape for LiDAR is constantly changing. Advances in photonic integrated circuits and silicon photonics have the potential to take LiDAR to the next stage of LiDAR on a chip, LOC, with the right cost, compactness, and scalability. This talk will provide a brief overview and status of modern LiDAR technologies and systems. Various solutions will be introduced and compared, and an overview of the market, challenges, and trends for automotive LiDARs will be covered. So with that, I'm going to hand off the presentation to Dr. Khanna.
Okay, thank you very much, Utkarsh, for your generous introduction, and welcome everyone for joining this talk. Now I have to see how do I get onto sharing, right? Share screen. Okay.
We can see your slides, Dr. Khanna.
Do you see?
Yeah.
Yeah, I think we're at the same point to take it to the presentation mode. Last time we had to make a couple of slides and then we were able to do that.
Tap the F5 key. Function
Yeah.
right at the top of the keyboard.
Yes, that's what I'm doing. But just doing F5 does not give me my notes, right? Why? What's going on? Oh, that's what I was afraid. I'm trying F5. Oh, yes, no?
Yeah, you're in presentation mode now.
Right.
Yeah, but this is not the right mode. Yes, okay, finally we got it, sorry. So once again, thank you everyone for joining. And I will start with taking you back, say 50 years. I was in a school in India and I was, being introduced to electromagnetic theory. And that was the time I saw the news in a magazine that the scientists in United States have sent electromagnetic waves to the moon, a pulse of electromagnetic waves, and by its return, they measured the distance very accurately. Now, 285,000 miles with an accuracy of inches. It was remarkable. I was very, very impressed, and I was kind of looking at the electromagnetic theory and saying, oh, it's very rough subject. And here, this news comes very timely. It gets me excited. It's very inspiring. And that made me kind of continue in that field. But I want to show you what it was which got my attention that time. So this is actually the Apollo 11 mission. Many of you probably know about this, not probably a surprise. This mission was in 1969, and the astronauts kept this retro reflectors. This was not called LiDAR. I think at that time it was called laser ranger. So the laser ranging. So this is a lunar laser ranging retro reflector project. So that is, it is a 0.5 meter by 0.5 meter reflector, which is made of 100 corner reflectors. Corner reflectors are an amazing component. If you can, many of you might know. So that the main property is that if the beam is coming into a corner reflector, it will go back exactly in the same direction. So it is not going to be scattered around and then a very tiny bit going back. Most of it will go back at the same angle. So this enabled them to measure the distance, and that is exactly the basics of LiDAR. That was, these results were coming in at that time in the early 1970s. Just for the sake of completeness, they actually used 694 nanometer signal. It was a ruby laser, and the amount of the power they used was 60 joules per pulse, which corresponds to something like 7.2 kilowatts of power, you can see. And that means that many quintillions of photons were beamed towards the moon. And the alignment was not easy, but they were able finally to do, as you can imagine, quintillion means actually it is more than 1,000 trillion. So that many photons, and they get back, imagine a couple of photons. But those are enough to give them the timing indication that what time did the pulse leave and what time did they come. So it's very interesting that it was done like 50 years ago. So with that, I move on. So we'll be talking about the need for autonomous vehicles. I'll introduce LiDAR. Many of you may be, experts already, or maybe may know about it, but I think one of the objectives here for my talk was to bring up the, people who are out of the field, like, microwave people, and bring them up to speed on this application. Because what is happening is that there is a lot of activity in this field. And I think engineers will have a better perspective, and they hopefully some of the people will say, okay, let me try. So we'll go through the block diagram, some information about the optical components used, the different types of LiDAR, and then market and trends, what's going on, what are the challenges, and what is next. Some of these will be just my own, like thinking what I think will happen. So this is the agenda. Now, let us talk about the sensors. Now you might see the car is getting filled with sensors. And to give you an idea, a modern car with the combustion engine has somewhere from 100 to 200 sensors overall. And the ADAS related sensor, the driver's assistance, they are soon expected to be 20 to 30 per car. That's a lot of sensors. And to give you an idea that the number of cars in the world are about 1.25 billion. And there are 300 million commercial vehicles. So even if like 20% of these cars start using ADAS sensors, there is a need for a huge number of billions of sensors needed in the next decade. So now the need for autonomous vehicles. I have a slide on that. I'm not going through all the detail, but one thing which comes out very clearly is the reduced number of accidents. We lose 1.4 million people worldwide per year in vehicle collisions. The majority of these are due to human error, and they are mostly pedestrians, motorcycles, and cyclists. It's a big number. Compare this number to the deaths caused by coronavirus in about a year, 1.13 million as of this morning. It becomes pretty obvious that we need to do something for the autonomous vehicles and try to control this number, which is very unreasonably high. So that is one of the functions which autonomous vehicles will do. And I think those of us who will participate in that effort, I think that will be a good feeling. So there are so many other applications of why do we need autonomous vehicles. I'm not going because that's really not the subject, but I'll just show you the list of those. There are so many. Transportation, accessibility, travel time, effective. So many numbers, many applications which will happen, and they call for autonomous vehicles. Okay, now these are the ADAS sensors you will see. This picture shows different types of sensors. They are actually marked down also. There are ultrasonic, which are the red ones. You can see that is on the sides, and particularly for the park assist and parallel parking. And then there are short or medium range radar, the gray ones. There are 1, 2, 3, 4, 5. Now this is not a standard configuration. This is a possibility and one of the scenario. There are so many different scenarios. Some scenarios need just a very few sensors. This has probably the most sensors. You can see there is a long range radar, and then the yellow ones is the proposed, I would say they don't exist right now for the LiDAR. So there is a LiDAR and radar both getting in the front for the long ranges, like for example, 200 meters and 300 meters. And then on top of that, there is camera, which is playing a very important role for giving the perception around the car. So it can show what all is going on. These are the eyes for all these things combine and give you a complete picture of what is going on around the car. And more recently, I have heard, at least I have read, that they are looking at adding, maybe they've already added a mic, like the sound sensor, which will also detect any sounds, like a sound of a police car or an emergency vehicle or some announcement. So that is interesting. The cars will have not only eyes, but also ears. Okay, so the next is the automotive sensors comparison. So there are three main ones which we are looking at in this slide. That is the LiDAR, radar, and camera. The sensing, and some examples are on the right-hand side of these LiDAR. The sensing dimension for the LiDAR is 3D. Radars are mostly 1D and camera is 2D. Now, I would like to mention that on the radar also, a lot of work is going on the imaging radar, which will change things, but we don't know how much. We'll have to see what the performance comes out to be. But today, most of, or practically all the radars, or auto radars, millimeter wave, are all 1D. So the range-wise, LiDAR is at about 200 meters and the radar at 250, camera is about 100, again in very good weather. So there is a field of view. I think this you can see that say, there are some things better in one, some things better in the other. So that's the reason, because there is no perfect solution. So complementation is critical. So, it is pretty obvious that diversity will play the role here, and we will have multiple types of sensors in the final version. And that too under the, like a lot of work is going on the sensor fusion. So maybe there will be devices which will be combining 2 or 3 of these functions as well. So just looking at that on the adverse weather conditions, radar is really the best. It will give you the information, and that is actually one of the main advantages of that. But radar is limited in the resolution or the accuracy what you can get with LiDAR. On the other hand, camera can read sign, it can see the color, and principal application as it shows that LiDAR is more useful when you're doing a pedestrian protection, because LiDAR can tell you, particularly the FMCW LiDAR, that the pedestrian is moving or standing, or the arms are moving at a different speed and legs are moving at different, so that you can get a good perspective. While the radar is good for obstacle detection and cruise control, and camera, principally, it will do a very good job of reading the sign, texture analysis, and can give you a good perception in the near range under good weather conditions. In terms of ASP, I think this LiDAR is still very expensive. It is not yet ready for the prime time in consumer cars. It will take time, but it will happen. Those who have worked on radar for a long time, they know that how expensive it was, and now it is already in production going below $100. So similarly, the target for the LiDAR is at $250. So one thing I do want to mention that LiDAR sensors, they do enable classification of the targets and detection and monitoring of 3D objects in real time. And what they have is a reliability, performance, and accuracy which is really unmatched. So at the end of the slide, I want to mention that it is expected that LiDAR will be one of those choices. Okay, here we are looking at different levels of self-driving cars. Those in the field, I'm sure they're very familiar with. The level goes from 0 to 5. These are the Society of Autonomous Engineers, or Automotive Engineers, sorry. And there are different levels of that. Level 1 is what it used to be, manual. Everything is manual. Then level 1 has some assistance, like could be cruise control or automatic braking. And then level 2 will have more features, particularly the stay in lane feature, which means it can guide it to remain in the lane, self-parking, and of course, the feature of level 1. And then level 3 is actually at this time, we are beyond level 2 in general, technology-wise, and enough cars are there to prove that yes, that technology exists. However, the number of cars are still in a very small number at this time. Now, the level 3 is the first level, which is called conditional automation, where it is called automated driving, because even though driver is necessary, but it is not required to monitor the environment. The driver must be ready to take the control. That's the main difference. Then the next level is high automation, where the vehicles are able to intervene themselves. There's a problem or they have to do something or take action, they will do themselves. However, if needed, human intervention can still be brought in. That will be an option. For example, some people will not feel comfortable. They are driving level 4, but they will know, I do want the access to control the car or stop the car. So finally, this is the full automation level 5. That's the one where the human drivers are completely disintermediated. No steering wheel, no gas and brake pedals, nothing. So that it will take time. So I think gradually things will continue moving in the right direction. And as per one of the marketing research company, ABI, is expecting that by 2025, there will be more than 8 million vehicles on the road with level 3 plus capability. You can see that the LiDAR is marked here on the bottom, that somewhere in the level 3 and above, LiDAR will be a strong option to consider. So LiDAR, those who are not familiar, it is an optical device. LiDAR, first of all, it stands for light detection and ranging. It's an optical device which can be used to measure distance, angle, velocity, and reflectivity of a target. Now it uses laser pulses or the frequency ramps in the infrared region of 850 nanometer to 1550. This is the range, but the RF people always talk in terms of frequency. So I have put the converted frequency numbers there too, that from 193 terahertz to 352 terahertz. Now these are, you can imagine when we're talking of, you will see a slide later, that very different frequency compared to the radar. LiDAR functions very similar to radar. It uses light instead of RF. You know, this automotive millimeter wave radar is 77 to 81 gigahertz today. And there is some work going on the next higher frequency at 140 gigahertz. But all those frequencies are far, far away from when we talk of 200 terahertz. LiDAR can generate very high definition point cloud images, and at the same time, it has the capability of classifying the object. That's a big deal. So as I said before, this is very attractive, or I would say necessary for the self-driving car for level 3+, due to its high resolution and excellent precision, which is not available in any other form. There are some examples on the right-hand side for some of these LiDAR. A brief history, won't spend much time. Originally, laser was invented in 1960, 1970. That was the experiment with moon we talked about. Then came 1970. That is when the solid state laser was developed and started being used. And at the same time, very low loss fiber also was developed and made available completely independently. But these two combined in that time frame gave a major boost to the optical and photonics world. LiDAR has been used in large number of applications since. It has applications from the airborne LiDAR systems, because where they go and survey the ground and get a complete picture of what is on the terrain. And more recently, technology has driven the cost to a point that it looks like it can be used in the automotive application. So at least the roadmap is shown. There is nobody there right now selling this LiDAR for automotive application for 200 meters at $250. But it seems like on the roadmap, it is a possibility. Then the first commercial car with LiDAR, some of you will know, was Audi 8. And that was a couple of years ago, which was released in Europe, not in the United States. So people have not probably seen it here. Another thing is that a lot of money is being invested in the LiDAR related activities. And now billions of dollars are going in, or they have gone into a number of startups. We will see some more numbers that what is happening. There are more than 100 companies working on the LiDAR at this time. Now here is the spectrum. Where we are, you see there is a microwave and millimeter wave spectrum, which is 300 megahertz to 300 gigahertz. And the infrared, that is what we are talking today, that starts from 300 gigahertz to 430 terahertz. It's a huge spectrum there. And of course, the visible is between 430 to 790, just an octave type of frequency range. That is the light which we see, the visible light. And you see this chart here. So between infrared, then we see that there are a number of segments there. And that is near infrared, short wave infrared, medium and long wave. So our action in the field of LiDAR is mostly in NIR, and it goes part of the short wave. Because as you can see, it is 750. It shows NIR is starting from 750 nanometers, and LiDAR are generally starting at 850, and they go to 1.5 at this time. Okay, now we will look at the principles. So one of the things is the LiDAR equation. Many of you are probably familiar with radar equation. So it is very similar, just it's a different terminology and slightly different way of calculating things. So the LiDAR equation, when the signal will go and come back, and the return power is going to be the transmitted power times the scattering cross section divided by 4 pi, and then that term inside, which represents the transmitter area times the receiver area, and the wavelength times the distance squared and the whole thing squared. So this equation will give you the received power. And for the spot, which is smaller than target, which is generally the case, the scattering cross-section is related to the target reflectivity by the relation in the second equation. So combining those, you have a simplified equation that the received power is equal to transmitted power times the target reflectivity, the aperture of the receiver divided by 4 pi length square. It's a relatively simpler equation now. And then if we assume that reflectivity is 10%, and the distance between the LiDAR and the target is 200 meters, the transmission power is 100 milliwatts. Actually, really the transmission powers at this point are tens of milliwatts, and the aperture is 1 centimeter square. The power received will be 2 picowatts, which represents for the microwave people minus 117 dBm. But I think the photonics people relate more to photons. So you can convert it with the equation using the Planck constant into photons. So this will turn out to be 15 photons per microsecond. So that's how you calculate the received power, and you want to make sure that your sensitivity of your receiver is better than that. Now, if you want to improve, if you look at the equation, you need to increase the aperture, but there is a limit to that, how much you can increase. Or the second thing is the power. You can increase the power, but that again, due to thermal conditions and the eye safety issue, there is a limit. You cannot do that either. So it is a challenge, and I think that's why the effort is going on better sensitivities and more efficient systems. Another thing I want to bring up is the beam spreading, which I did allude to in the beginning, that the beam divergence theta is typically given by, it's approximately, not exactly, but it is approximately wavelength divided by the diameter. So if you look at the radar, which is at 79 gigahertz, center frequency at least, the wavelength corresponds to about 4 millimeter. And with the D is equal to 10 centimeter, typically, the beam divergence is 0.04 radians, which corresponds to that the beam at 100 meters will become 4 meter wide. It's pretty big. So for example, from a car at 100 meter or 200 meter, you will get only probably just 1 point back. As far as the LiDAR at 200 terahertz, the wavelength is 1.5 micrometer. And with the diameter even at 1.5 millimeter, which is very typical in this frequency range, the beam divergence is 0.001 radian, which is, it is 10 centimeters at 100 meters. That is the reason that it has a much higher resolution and much higher precision. Now you could, like again, get better divergence by increasing the aperture D, but it is really not practical. You can't have a huge antenna there. Okay, I think that's this one. Okay, and now I think I just mentioned the LiDAR eye safety concern. So this is also an important point. Even though there are no real standards for LiDAR, but on lasers, there are standards which define the safety for the eye safety. Now, 905 nanometer, basically the lens and vitreous fluid will transmit to the retina. So there are strict limits as to how much laser power can be generated. The longer wavelengths are less dangerous. The lens and vitreous fluid will absorb 1550 and block it from reaching the retina. And it is 10 to 40 times higher eye safety at 1550 compared to 905. So the longer wavelengths are preferred. So that is one of the advantages. People say that people who are using 1550, that it makes the life simpler because they don't have to worry about the eye safety as much as the 905 LiDAR. So here is a simple basic block of a LiDAR. What is included? What all is there? This is, for example, you heard the word time of flight, which normally means a pulsed LiDAR. So starting from the left, you have a control hardware, which controls actually all the components here. So there is a laser modulation circuit that you drive the lever through a lever driver. And that is coupled to the optical beam. So the beam will be projected from the lever to the beam steering component. And there, the beam steering can change the angle of the beam and can direct it to wherever you would like it to go. There is a transmit optics on the way to basically condition the beam for the configuration. So on the reflection side, the beam is scattered and a tiny part goes back. That's what we were saying, 10% reflectivity, or actually it is even lower. That goes back through the receive optics into which enables the signal to go back to the photodiode array. So the photodiode will detect it and then go into the receiver and processing FPGA and ASICs before going to the control hardware and in the output. So the next slide shows.
I'm sorry, Dr. Khanna, there's a couple of questions. Jay, do you want to read those out?
Sure. So there's actually one question for me here. It was similar to RF and microwave. What are the noise constraints? What are the noise sources that would impact your measurements?
Yeah, it is not like the RF microwave that we can improve the noise by putting an amplifier in the front, right?
Right.
So here, actually, it is the type of detector which is very critical.
Mm-hmm.
Okay, so now there are detectors which have very low sensitivity. And, like these are the single photon avalanche detectors. They are, for example, or the silicon photomultipliers, they are able to detect very, very small signals. And that helps. Otherwise, you are right, the condition for the noise, for example, it becomes very challenging when in the sun, and sun also interferes with some of these LiDAR. So it can come and interact, and the noise can, go above the signal level.
Right.
So either you have filters there. Filters can be added, at least under certain conditions, to reject the interferences. Or the power is increased for the transmission during that time, not all the time, because that has its own consequences. So that's how it works, to my knowledge, at this time.
Okay, and then the environment, I imagine, if it's raining or I think that has an impact as well, right, on LiDAR?
Yeah. No, that is true. That LiDAR is sensitive, and we will talk about that. Yes.
Okay.
There is an effect there.
Okay, thank you. We have one other question here from Sarush Rusty. And his question was, how is the beam steered and what is the speed of the steering?
Now, how the beam is steered, we will be looking at in some slides later. But it is, for example, there are mirrors or the MEMS, which are controlled, and they move the beam, or there is optical phased arrays, and I think we will be talking about a little later. That you see, I'm showing here in this technology, there are 3 different things. We'll talk about this. I have a couple of slides on each, and I think it will be clearer.
Okay, thank you. I think there was a question we have at this point with Kosh. Go ahead.
Before I hand it back to Dr. Khanna, I've sent out a few messages to some people asking for their information so that I can check them in. That's because my information doesn't match the name that they used. Please check your chat window and see if you've received a private message from me. If so, please respond to that. Thank you very much. Yeah, Dr. Khanna, all yours.
Okay, so you are asking me to check?
No. I've sent messages out to some of our audience members asking for their information so that I can check them in.
Okay,
So,
okay.
yeah.
I don't have to do anything.
Nothing, no.
Okay. So coming back to the slide, there are, like 3 aspects. I mean, there are many other parts of this LiDAR, which we are not talking about. That is the digital circuitry, analog circuitry, CPU, data management, ML or AI. We are not talking about those things, but the front end, there are 3 aspects. One is the source, and then second is the detector, so basically the transmitter and receiver, and the third is the beam optics, what comes inside in between the source and the beam going out. And similarly on the receiver side also, you may need some beam optics. So in terms of sources, there are 2, as you know, we are working at mostly when we talk of LiDARs today, we talk of 950 nanometers and 850 nanometers, which fall in the near infrared, and then 1550, which goes in the short wave infrared. So there, the laser diodes, so semiconductor lasers are used. At the lower wavelength, it is the gallium arsenide, and at the higher 1550, we have used indium phosphide is used. So again, the laser which is used for FMCW, of course, you need some tunability there, so you can modulate that. You can change the frequency, which is, of course, electronically, the laser frequency can be changed electronically or with temperature. Now, temperature is not fast enough. So, there are electronic ways of changing the frequency because the amount of frequency you need to change is not that large. And then there are other methods, whether it is through PLL or through IQ modulator, the frequency could be controlled. Then there is VCSEL. This is a surface emitting vertical cavity laser. This is again in the NIR region, more in NIR region. And we'll see a little bit on that in the next slide. Then in the beam optics, there is either the LiDAR which scan, or there are one which are no scanning, which is called flash. And in scanning, you have mechanical scanning. That was the question, right? How do the beams move? So there is a mechanical scanning, there is a MEMS scanning, or there is optical phased array scanning. And in flash, of course, there is a very narrow pulse laser. We'll talk about the flash, that there is a separate slide on that. And then there is a detector part, which is the receiver, same thing, but there are 3 types of receivers. Generally, the most elementary is the pin photodiode, but the receiver which is most commonly used is the APD, which is the avalanche photodiodes. And then there are SPAD and silicon photomultipliers as well. These are more sophisticated detectors. So we will see a little bit on these as well. So this shows the classification of what all is there in these subjects. So, okay. So laser is a device that emits light through a process of optical amplification based on stimulated emission of electromagnetic radiation. What it means is that the light, as an example, the light produced within the laser medium, the core medium which has the gain, it will bounce back and forth between mirror, that is one of the configuration, stimulating other electrons to fall to the ground state and release the light energy. That particular process is called stimulated emission. So semiconductor lasers are the laser diodes which are pumped with an electrical current in the region where N-doped and P-doped semiconductor material meet. You see a picture on the left-hand side on the bottom. So there are two classes of the lasers. One is the edge emitting laser and the other one is vertical cavity surface emitting laser. We will see in the next slide. So some different types of laser diodes. There is Fabry-Parrot cavity, which is a standard cavity and with reflecting mirrors, which I just mentioned that the signal goes back and forth. In some ways, it is similar to that you have microwave amplifier and you have a resonator around that and it will start oscillating. So the basic concept will be the same. Then there is a DFB, which is distributed feedback. And the active region of this device contains a periodically structured element that builds one-dimensional interference grating, providing the optimum feedback to make it oscillate. The edge emitting laser have an elliptical beam, and the VCSEL, on the other hand, actually the VCSEL and DFB have wait a minute, elliptical beam comes from the Fabry-Parrot and DFB, while VCSEL is the one which is the perpendicular, the signal goes perpendicular to the surface. It is a vertical cavity. It consists of the distributed Bragg reflector mirrors, and it typically functions at this point between 650 and 1300 nanometer on gallium arsenide. And in this case, the beam is circular and it is vertical to the junction. The other two, the beams are elliptical, so they have to be modified a little bit. So here are the detector examples we talked about. So photodetector basically converts the optical power to electrical power by photoelectric effect. Photosensitivity that describes a photodetector's response is a critical characteristic, and it is a function of the wavelength. So the pin photodiode, which is the most elementary of these detectors, is a reverse bias photodiode, which causes absorbing photon to generate a current gain of 1. The next one is the APD, which uses the reverse voltage to multiply the photocurrent through avalanche effect. Silicon-based APDs function to about 1100 nanometers, sometimes a little less than that. And the in-gas APDs take us to 1700 nanometers. And APDs have a gain of less than 100. You see the picture on the bottom right, which shows the log of gain versus reverse bias for a PN junction. So it is the same PN junction, but it is design a little, there is a design issues, but more importantly, where it gets biased, that determines that how you are using it. With the first part, which mu is equal to 1, then we have the APD part, which is the linear region. And then next is the Geiger mode, or this is called digital mode because it is just 0 and 1. That one is designed to, if you look at the SPAD on the left-hand side, the single photon avalanche diode, it is designed to operate above the breakdown voltage. And it provides you, again, huge gain of 10 to the power 6. But it is limited to digital 1-bit operation. It can, however, get integrated into the CMS technology. So that is what is called the SPAD detector. Then the last one is the silicon photomultiplier that actually integrates, it is same as the SPAD, but it integrates a number of pairs, can be a large number of pairs of SPAD with resistor in a dense array And that way it provides the it can control the magnitude of the instantaneous photon flux. So it is no longer 0 or 1, it can give you a linear information. So now we are coming to distinguishing features of LiDAR. Let me see how we are doing on time. We are okay. We are.
We're good.
Okay, yeah, because I have quite a few slides. I have to maybe rush through. So the distinguishing feature of LiDAR. So there are three different things we have to watch out. That what do we want? What should we choose? One is what kind of distance measurement we want to do, which means we want to use a pulse LiDAR, which we call time of flight. Do we call amplitude modulated continuous wave or FMCW, these three. So for example, in autonomous vehicles, time of flight is the one which is being used today in the experimentation, and in the LiDAR market overall, time of flight are the ones which are, which cover the vast majority, I would say more than 90%, 95% is time of flight today, production. However, FMCW is relatively new, but it is picking up speed. So that we'll have to watch that how things go in the next couple of years. The laser wavelength, as I mentioned before, these were the three wavelengths. You have to pick up one of these. Then again, that depends upon what kind of modulation have you chosen, what is the application, and the cost. For example, the 1550 nanometer is significantly more expensive in terms of technology than the 850 and 905. There, a number of components can be on silicon and can be integrated easily on silicon photonics. And lastly, as we talked about a little bit, that the beam steering technology, which is, has to be decided that you want a spinning LiDAR, you want mechanical scanning, you want OPA or flash. One of the scanning picture is shown here on the right, and you can see that it is like line by line. It's a scan which will draw the pattern. So one thing I like to mention that so far we had seen mostly the linear scans in this application for LiDAR, but lately some people are experimenting with completely non-linear scans. Like there is a company called LiVox. So that's very interesting to see. People are coming with novel ideas and say how, making involved scanning patterns or protocols. Now, this slide represents the mechanical scanning automotive LiDAR. This shows, I probably won't go through everybody, all of these, but on the left-hand side, you will see the LiDAR. This is a mechanical scanning, and this is the one which was used in the A8 Audi, which was released in 2018, it says 17 or 17, 18. And it is capable of traffic jam assist, and it is the only LiDAR available which was used in the consumer car. And I think now there are a number of others which are getting ready. Then there is a mechanical LiDAR for robotic cars, and that is completely mechanical. This is mechanical scan. It is rotating. You might have seen on the top of many cars here. This is a Velodyne 350-degree rotation. And they are bulky, and they're really not meant for ADAS kind of application. But there are a number of other applications where these things are playing an important role. And then there are some other slightly different way of mechanically moving the scanning. So this slide shows some features of OPA versus flash versus AMP. So OPA, which is the optical phased array, we'll see a picture in a little bit, that this has a continuous beam steered by the optical phase modulator. It has a better, or I would say superior form factor, as lever is on a chip. So it is all on a chip. And it is dynamically adjustable scan rate, resolution, and zoom, which have a number of different applications when you can independently control resolution and zoom. We are like, if you want to see a particular part of the scan in under zoomed condition, you can do that. So higher data collection rate with multi-beam scanning. Flash, on the other hand, we talked a little bit about, is like a digital camera, which illuminates the environment with a single laser pulse. But it have issues with the vibration effect or high power consumptions. You can get either long range but expensive, or low cost and short range. MEMS, which have been very popular actually, there are number of, you can see some of the vendors are listed on the right-hand side, and it moves the laser by cascading the tilt angles of multiple tiny mirrors. So these are the MEMS mirror, but once again, its alignment is susceptible to shock and vibration, then which becomes a problem when you are talking of using it in the consumer cars. But there is a potential under certain condition to be used. Then they have fixed scan rate and resolution, and they have a blind spot due to the minimum range. That is another, because of its speed, how fast you can move it. Certainly, it is an expensive technology. So there are a number of vendors who are working on all of these technologies, as I mentioned, and hopefully there are going to be some winners here. So this is one more slide just to give you, again, a comparison in on scanners in a table form. So the working principle, main advantage, and only just simple three things. Mechanical scanners, they can be of, galvanometers, the galvanoscopes, or rotating mirrors and prism. They are one way of doing the mechanical scanners. Their advantage is that you can move 360 degrees. However, as we talked before, they are bulky and a lot of moving elements there. The MEMS we have talked about, it's compact and lightweight, and but at the same time, power management and linearity of scanning is an issue. Optical phased array is, as we talked about, was a phased array of antennas. This is a fully solid state. But one of the issues which at least I have heard, is that when you want to couple the phased array elements with the rest of the optics, that coupling mechanism is still being worked out. At this point, that coupling is limiting, actually. It is weak, so losing a lot of power in that coupling itself. Flash, on the other hand, it is potentially very fast frame rate, and it has, pulsed flood illumination. However, this does have a limited range, because you take a laser and you diffuse it and you try to cover a large area. So the power comes down very, very quickly with distance. There is a list of the MEMS players, some of the MEMS players and some of the OPA players on the bottom. And these pictures show on the top the optical phased array. In the middle is the MEMS, which will change, you can move the mirror and you can change the direction of the beam. And lastly, at the end is the mechanical scanner. So this is actually, which is now becoming, there is a lot of activity going on. A number of universities, a number of vendors are trying to do OPA because it has potential. I think the issue is still the cost and some technical challenges. But it is high efficiency configuration and completely solid state 2-dimensional beam steering. It is used in lens-free LiDAR and free space communication. It can be used both for transmitter and receiver, and it does have a high performance using low loss photonic components on like chip, waveguide, phase shifter, optical antenna. As it is scalable to centimeter scale aperture, and it is integrated with on-chip detectors and CMOS electronics. You can see on the right, it is very similar to in microwave, you have the phased array. There are phase shifters, which are again shifted electronically, electro-optically, or one option has been doing it thermally, which is not very practical, it slows down. But the beam, by changing the phase, the phase of the different elements, the beam can scan the whole field of view. Now here is a point cloud of an area. This is with the time of flight, and it looks very strong. It is with a LiDAR from Quanergy, which have 1.3 points, 1.3 million points per second. I do want to clarify that points per second, that's a good way of figure of merit for a LiDAR, which is calculated by multiplying the frame rate with the number of points in the vertical direction times the number of points in the horizontal direction. So, and then it does have the centimeter level range accuracy. One thing, however, to note that this is not the information coming out of single scan. This is multiple, I don't know how many, but there's a large number of scans to come to this type of a point cloud representation. Now, a flash LiDAR, I want to just close a little bit on that, that in this case, even though we have talked a few times, this beam is not scanned. The scene is illuminated by a diffuse laser source, limiting the range. Array of photodetectors is needed to form an image. It is just like a camera on the receiver side. It has a limited field of view and range. No moving part, so it is some ways it is cheaper, lower assembly cost. There is no mechanism for beam scanning or anything. Potentially higher frame rates and better spatial resolution. Now, one thing which has happened more recently is the development of multi-beam flash. That is showing a great promise. For example, Ouster have shown 120 meters range for 128 channel with 22.6 million points per second. However, there are a lot of challenges ahead. Not only the cost, but even technical challenges before it can have a broader acceptance. But this is a technology to watch in addition to the FMCW. So the flash players, some of the list is given here. You can see. Now we are getting to the FMCW LiDAR. Now FMCW LiDAR can reach larger distances than most pulse design. 300 meters range up to or beyond have been reported. The eye-safe, it measures velocity instantaneously, unlike the pulse radar. In the pulse radar, velocity is inferred. You will take frame by frame the information on the position of the obstacle, and you will infer the velocity, while the FMCW will give you instantaneously the velocity. It requires lower power, lower peak power lasers, and have lower consumption. Does not need to generate, like for example, the pulse radar may need 50 volt, 100 volt, 2 nanoseconds, few nanoseconds, which itself is technically like expensive and challenging. You have a higher dynamic range, very high precision of range and velocity measurement. This is very attractive for the LiDAR. It is interference resistance from sunlight as well as from other LiDAR. That again is a very distinguishing feature, and potentially right now that's not true, but potentially it has a lower cost, and thanks to the photonic integrated technology advances, and a number of companies are working on getting this to the final line. So this is the principle of operation. These slides, I have a couple of slides from Silk. Thanks. So if you look at the top, you will see that the LiDAR will send a signal to the target, and it is a ramping signal. It is a ramp, and it will go frequency modulated, and it will hit the target, and it will come back, and that in that when the signal comes back, there is a delay in time. So if you mix the frequency which is at the origin and the one which is coming back, you find the difference in the frequency which represents the range. If you look at here on the number 2, the returning chip will have the range, the frequency shift, as well as the velocity Doppler shift. That is the key, because when you have a ramp and then it comes back shifted in time, when you mix the original source as the local oscillator with the return signal, the frequency difference, that means the frequency difference from what the signal left at the time when it was triggered, and then the one which comes back, that difference will give the range. And then the second aspect of the Doppler that you can see in where it adds the frequency shift on the bottom of the middle graph here, that the velocity related will give another shift, but that shift is different for when the ramp is going up and the ramp is going down. As you can see on the bottom of the graph, this graphic, you will see that because of the Doppler, it is no longer symmetrical. So there is like a shift which is larger than the shift without the Doppler on ramp up, and it is much lower on the other side. So these two frequency shifts, when these are measured, you can add and subtract and sort out and determine what is the range, the frequency corresponding to the range and the frequency corresponding to the velocity, and instantly you get that. For example, this is on the left-hand side, you can see what is really happening physically, that there is a tunable lever, it is frequency modulated signal around the carrier frequency of 1550. And then a part of that signal, as I mentioned, local oscillator, comes to the mixer. And the same mixer is also getting the signal on the bottom, which is coming from the target, the reflected signal. So that signal comes into the receive optics and is taken to the mixer, and it will mix with the local oscillator and give an output, which is equivalent of getting a gain out of the mixer there of coming from both signals. So they get mixed, and that optical signal then, when it is detected, provides on the left-hand side a single nice the signal which represents the frequency shift. And once again, the frequency shift, it is can be used to determine both velocity as well as the range. One thing which is to be provided in key number 4, there is a unique unlock key, which actually means that no other signal can give you, will mix with the LO and give you the output which can be recognized by the receiver. So it has to be coherent. It has to be the signal which left, that's the only signal it will go in. So that's a very big advantage, and it really makes so much easier to get the sensitivity of the receiver. And then here you can see the same thing, that the signal is going out from the FMCW LiDAR and comes back, and it has all the information on this, and it is projected here on the right-hand side on the point cloud. So you can see On the top, this is the point cloud, which is coming from the depth, the depth only is the bottom side. There is only depth. So you can see that the person, when it's moving, you see only one color, while the colors on the background are also changing. So this is when there is no velocity component in the lower part of cloud which you are seeing. On the upper one, you can see that it is not only that you find the person moving, but you also see the velocity in terms of the colors are indicated, that the legs are, you can see, getting red, or the arms are yellow. So that element of velocity, because they are moving at different speeds, can be captured at the same time. This is a huge advantage, that instantly getting the velocity animal, velocity element from the LiDAR. And here it is showing once again that that only depth, or on the bottom it is the velocity, which means that if the person is moving, actually I think this is the video is not working in this form. But the lower, again, you would see that when the person is moving on the cycle, it will show you the different velocity elements, which will not be shown in the depth only. So once again, it does provide good performance at low cost, size, because of the integration. So here is, I think I'm getting to the last slide now, the time of flight versus FMCW. I'll be very quick here, I see. Position accuracy, you can see that it is excellent for the FMCW at 1550. So if you look at the time of flight, both one at 905 and at 1550, and compare with FMCW, you see that FMCW have more advantages, including the eye safety and interference rejection. However, the technology readiness is much better in the time of flight options than in the FMCW, where a lot of work is going on, but still there is more work to do. On the right-hand side, it shows the integration example, how that on a silicon chip, the active devices are mounted, and it makes it a very small, compact LiDAR system. So with that, I think I have a couple of slides, very few slides on the market. There are so many different applications for the industrial market. There is a mapping, there is security, I'm not going into the detail, or robotics, or smart cities and transportation. So these are the markets where the LiDAR is being used presently. Mostly it is used there. The ADAS, or the, for consumer cars, the volume is not yet there, as I mentioned. But for these applications, there are many companies which are already shipping in production for all of these applications, except for the ADAS is a very small number. And you will see the numbers also right now, that this is the market size based on the type of the market. So let us see, we are interested in ADAS vehicle. So that today is $19 million per year, which is not that much. But it is expected to go to 1.7 billion by 2025. On the other hand, the total market may only little more than double, but the market for the ADAS is going to increase very significantly. So once again, you can see that right now, ADAS is a very small, I would say, you can see the smallest part of the market of LiDARs when you compare with robotics, when you compare with topography, the wind, and the industrial applications. But things are expected to change within 5 years. So market factors, a lot of investment is going in. As of the latest count, there are 107 players who are in either production or in development phase. a significant portion of the new players is working on FMCW, and more lately it is the VCSEL-SPAD combination. COVID-19 has impacted the development for this technology, and the guess is that it is going to delay everything, by 1 year or so. So there is a list of the vendors here for the LiDAR, the active people and R&D player, and this by no means is exhaustive list. There are, as I mentioned, there are a lot more people in the game plan. This is just one slide on the market share, how the market size will be changing between 2019 and 2030. This is from the ID Tech Exchange Marketing Company. And you can see that in terms of the private vehicle passenger car, that is the blue on the bottom. And then there are private vehicles and shared mobility and delivery vehicle, the van and trucks. So there are but everything is moving up, and the size of the complete this vehicular market for LiDAR is expected to go beyond $5 billion by 2030. So we hope that happens. So this is another way, I'm not going through any detail, but this is another way to show that 905 nanometer and 1550 nanometer, who is busy and what type of LiDAR they are working on. The scanning mechanical or the solid state scanning or the flash LiDAR, or you can see there is a number of companies which are working on the FMCW part, which is, as I mentioned, more companies are working on FMCW. So one slide on the target emulation measurement. I'll be very quick on the challenges. The current test systems are manual. You can see that these are the corner reflectors, and then the LiDAR is, placed, and then it measures the reflectivity and angle and distance for different corner reflectors. Sometimes they will move the reflector as well. So it is not very practical, but that's what it is. And it is because there is very small volume at this time. This kind of practices are not scalable, and they need a large physical space. So while current LiDAR are largely time of flight, there are new technology we are developing, as we know. So what is needed is the flexible instrumentation solution to cover multiple emerging configuration and modulation for testing and emulating these LiDAR. Creation of the point cloud scenarios is necessary to emulate the real world scenario. So this is what it is now, the mechanics physically, and on the bottom is the system concept, where this whole thing can be done electronically, where the LiDAR signal will be manipulated and sent back and take the measurements, which will be scalable, and just like today already happening in the millimeter wave radar. So for the test and measurement, today there are some solutions available for the time of flight, but I think the work is going on for the FMCW in parallel with the development of FMCW LiDARs as well. So the trends, FMCW LiDAR is becoming more popular thanks to advances in photonic integrated circuits. VCSEL-SPAD combination I mentioned before is picking up speed, but major challenges lie ahead. ADAS applications are expected to continue to be a minor use of LiDARs over the next 4 to 5 years. That's the time when they are expected to pick up speed. Non-linear scanning, as I mentioned, are being experimented. The sensor fusion is getting a lot of attention right now, both from design point of view as well as the test perspective. And the trucks and public transports are likely to be the first ones adopting autonomy, and they will be the first one to use LiDAR. Of course, one of the main reasons is that they can handle a higher price, and that if the technology is ready and the price is acceptable, this will go. And lastly, that the level 4 and 5 autonomous vehicles are expected to have LiDAR in one form or another, even some of the later part of level 3 as well. So the last slide is the challenges and what next. Certainly we need a consolidation of vendors. Now at the last count, as I mentioned, 107 companies working. This is way too many. So there is a need to reduce probably by or merge or consolidate by an order of magnitude. And another thing is that how many types of LiDAR will make to the end. There will be one, there will be two, we will see. Then one thing which is not really there at this point is the standards. It is very important at this time that standards are set, because otherwise it is so hard to compare the different configurations. So once the standards are there under a particular condition, what is needed, what are the feature set, or what are the numbers for the specification, that will make it easier to compare the different LiDARs. So that effort is the people are talking about, but I have not really seen any serious effort going on in that direction. Integration efforts need to speed up. The LiDAR on chip, programmable photonic integrated circuits, there is an effort going on, but they have different application, but some of the application can be used into the LiDAR. And of course, artificial intelligence and machine learning, those things need to catch up as well. Now, another, what next? I would say that this VCSEL SPAD multi-beam flash, which I mentioned that we saw some good results from Ouster. We have to see how far it goes in terms of its performance and particularly the cost. Then scalable test emulation systems will be needed so that we can match up with the scaling of these LiDARs when they start ramping up. Then the chip scale FMCW LiDAR is emerging as a promising technique for long range, high resolution performance at the industry cost targets. That is a strong possibility that it might meet all the goals. And lastly, that the cost has to be below $250 in volume to make sense for the broad adoption, because there will be multiple of these will be used. So that is the target which I have seen people are asking for. So with that, my presentation is closed, but I started with the application of the moon, and in 50 years, the LiDAR have gotten into the iPhone. Now, these are the consumer application. LiDAR is now there in many of the smartphones. Samsung, it's getting in. And then now, last week, they announced iPhone 12 with the LiDAR functionality. In March, it was the iPad, and this last week was the iPhone 12. It uses the VCSEL SPAD combination, which is also being tried for the self-driving cars as well. And its application right now is from the iPhone. They are interesting, but still I think people are looking at what else they can do, but at least it will deliver depth sensing capabilities, supporting new photos and video apps, improved AR, and the ability to scan and measure rooms and humans. So in that light, the race for the iPhone apps is on. Number of companies are working on these apps, and probably there will be some application which we have not thought of yet. So
Dr. Khanna, we do have a couple of questions that, if I may.
Yes, so I think that's okay. We are done. This is, if there are a couple of questions, I'd be happy. I will try to answer.
Okay, so there's a question from Harshpreet Bakshi about, can you comment on the imaging, terahertz imaging, how that compares with LiDAR? I mean, it would seem to be a better solution, especially with the environmental issues that I mentioned earlier.
I really don't have that real comparison, but you know, this is terahertz imaging is a very different frequency. It is not into the same domain at all. So I don't think anybody is looking at that for automotive application. I think it's the way I consider terahertz imaging if we are talking of, 1 terahertz or below. That's the imaging I am familiar with, and that's really not, at this point, does not seem applicable for this application. But that has its own applications. There are a number of things which are going on in the terahertz imaging. Medical imaging is, for example, one of those. And I think there are other applications which are being explored, but not in the automotive.
Okay, so in the chat window, there are some product statements here that people are welcome to look at from Oster and Validin. A couple of other questions at the bottom here. Will LiDAR have challenges in detecting black color objects since they will absorb more of the NIR signal?
Yeah, it is true. So there will be a more challenge in doing that. I have not seen any study on that yet, but that certainly will be an issue.
And then another question here is SAE the natural source for standards, or AEC or European OEMS or others?
Well, it is not obvious. SAE does have standards activity, which is pretty solid. But I think it is a question of who is going to take the lead. It is very important that if we are expecting these things to take off in a couple of years, 2-3 years, the effort really does need to start.
There's another question here, which you may have alluded to with the iPad and the use of LiDAR in other commercial applications. But one of the questions that came up is, are there any use cases of LiDAR for microscaling images in medical applications?
Well, LiDAR has application in the medical world. The imaging for medical, for example, by using LiDAR, people are able to look at, very, very close with a very wide bandwidth. You can look at like at 1 millimeter distance, a few millimeter distance. So that opens up avenues to look at the, that is basically the biophotonic side of the laser. There are medical applications already. I think there is a effort going on. I think I may not have the detail, but I can confirm that there is work going on for the medical application.
So there's one other question here, which was, is FMCW system similar to flash type with one illumination source and camera sensor like detector?
Actually, FMCW and flash are really not the same. Flash is generally, it is time of flight. It is the modulation is different. Flash, it is more like camera. It is it is not FMCW. Flash is the time of flight. It is just the whole surface in the front is illuminated. And when it comes, the receiver is more complex in the flash type to recover which direction the signal is coming from. But the FMCW is the modulation, which is, these two are not combined. I have not seen anything that is, even if it is practical.
Okay, so we have another question here from Michaela. What is the minimum reflectance of a surface that that has to provide over certain angles of incidence?
I think that depends on the condition, right? I mean, typically the reflectances for the optics is not that much. On a typical target, there are single digit is the reflectance, 5%, 5% to 10%, sometimes even lower. So certainly that is a challenge.
Okay. And then going back to terahertz, how much power can you get out of a terahertz light source?
Terahertz, again, I don't know what terahertz is it we're talking of, the 1 terahertz, or, there are different, I really don't know the answer to that question, but it is probably, if you're looking at solid state application, we are talking of probably tens of milliwatts.
Okay. And then another question that sort of goes back to noise. Bruno Acklin was questioning what is this, the signal to noise ratio of coherent LiDAR, like FMCW, suffer from, does the SNR of coherent LiDAR, like FMCW, suffer
yeah,
from
I think
speckle noise?
I have been told that FMCW LiDAR at 200 meters have been detected with 15 dB of SNR, which is very amazing actually. But these are again experiments, not into any production LiDAR, which is amazing, I would say.
That was the last question. I don't see any other questions. If anyone does have a question,
I think
may
there
have
was another question early on. It had to do with the cost. So the question from Jay Mullins was, has the cost come down for 1550 nanometer laser sources?
Oh yeah.
I'm not really up to date on how fast the cost is coming down, but I think the way cost will come down is not just the laser, it has to be integrated into the next level. Yeah, it is hard to reduce the cost of laser by itself because it will not be possible to meet the overall target. It will be integrated. It will be integrated into silicon photonics, then the new ways of putting the gain core of indium phosphide on that and getting 1550 out without adding a lot of cost on that. That the challenge is going to be the integration to get the cost of the LiDAR down, not just the laser by itself. Because laser may be divided into two parts. Part of that will be on the silicon chip, the feedback, for example, and then the core material, which has the gain, will be dropped onto the silicon waveguide. So I think there are a number of things there are a number of companies, some of them I know are working on these challenges to bring, because everybody knows that the present price point is not right. So the only way is the LiDAR on a chip. So that will include laser.
Okay, I think that was pretty much it in terms of questions. I want to thank everyone's attendance. This has been a great talk.
Yeah, I have my email. Yeah, I think I don't have, but my email address is there in the announcement. So if there is anybody who wants to get in touch with me, I'll be happy to.
And we can send that out as part of the email when we send out the links to the video and the slides. We can include your email for any further questions.
Great.
Sure.
So I wanted to thank you, Dr. Khanna, for your time.
No, thank you very much.
Great,
thank you, everyone. I know some of the people are joining from different parts of the world, so I'm really thankful to all of you who attended. And I know there are a lot of people who could not attend. I got even the messages, so they will get the link and they will probably look at the recording. So thank you, everybody.
Okay, Utkarsh, if you didn't have anything else, we can.
Thank you to the organizers.
Yeah, so I just wanted to once again thank everybody who attended. I hope you guys found this as informative and exciting as we did. Thanks again, Dr. Khanna. This was very informative. I'm pretty sure you'll be getting a lot more questions via email soon. So yeah, in closing, just wanted to mention this is one of the best attended talks that we have done. We had over 460 registrants from all around the world, and it was, I would say, particularly good this time because our core area for this chapter, the MTT-SCV chapter, is the Santa Clara Valley, San Francisco area, and we had about 210 registrants from this area, and the live talk itself had close to 135 people on Zoom and about 5 to 10 on Facebook. So more than 140 people attended the live talk. And I'm pretty sure once it's uploaded on Facebook Live, on Facebook, on the MTTS Facebook channel, it'll benefit a lot more people. So thank you, everybody. And we will be doing one more talk this year. That talk will also be in the field of photonics. We'll be sending out the information for that. So if you registered for this talk, then you're part of our email list. You will be getting information about future events. So thank you again, and stay safe, and we'll see you all next time.
Hey, thank you, folks. Thanks, Utkarsh.
Thank you.
Okay, bye.